The edge of vision is not a line. It is a horizon that curves and fades, never quite meeting the boundary we imagine must exist. In the farthest reaches observable to human instruments, light arrives from distances so vast that time itself becomes a substance we move through, dense and slow, bearing the imprint of epochs long collapsed. We stand on a small sphere of rock and water, orbiting a middle-aged star in an unremarkable arm of a spiral galaxy among hundreds of billions of others, and we point our lenses outward into the dark. If you're watching this, consider filling your screen entirely and staying with us as we move deeper into what has been found. What returns to us is not merely light, but information encoded in wavelengths stretched by the expansion of space itself, a story written in spectra and shadows, in the subtle bending of rays around invisible mass, in patterns that repeat across scales so enormous that the mind struggles to construct a frame large enough to hold them. The James Webb Space Telescope floats in a gravitational balance point nearly 1 million miles from Earth, positioned where the pull of our planet and the pull of the Sun meet in equilibrium. It does not orbit Earth. It orbits the Sun alongside Earth, maintaining a fixed relationship to both, a geometry that allows it to stare into the same patch of sky for weeks or months without interruption. Its mirror is gold-coated beryllium, segmented into 18 hexagons that unfold like a flower after launch, aligning with nanometer precision to form a single coherent surface 6.5 meters across. This mirror does not see visible light the way human eyes do. It gathers infrared radiation, the heat signature of ancient things, the redshifted glow of objects moving away from us at velocities that approach the speed of light itself due to the stretching of space in which they are embedded. Infrared vision allows us to peer through dust clouds that would otherwise obscure entire regions of the cosmos. It allows us to see the thermal glow of stars forming in collapsing clouds of gas, galaxies assembling in the first billion years after the beginning, and perhaps most importantly for what concerns us here, the deep architecture of matter distributed across the largest scales the universe permits. What has come back from this instrument in its years of operation is not simply a collection of pretty images, though the images are extraordinary. What has come back is a cascade of data that forces cosmology to reconsider assumptions embedded so deeply in the field that they have begun to feel like facts rather than models. Among the findings that have emerged, none is more conceptually unsettling than the apparent detection of structures that seem to loop, to recur, to appear in multiple locations separated by distances that should render such repetition impossible under the standard understanding of cosmic evolution. These are not small structures. They are not clusters of stars or even clusters of galaxies. They are arrangements on scales exceeding 1 billion light-years, formations that span significant fractions of the observable universe itself, and they appear to exhibit patterns that suggest either a topological peculiarity in the shape of space, a breakdown in the assumptions underlying our distance measurements, or something else entirely that current theory has not yet anticipated. To understand what this means, it is necessary to first understand what the universe looks like at the largest scales we can measure. When we map the distribution of galaxies across billions of light-years, we do not find a smooth, uniform fog of light. We find structure. Galaxies cluster together in groups of tens, hundreds, or thousands. These clusters themselves gather along filaments, vast threads of matter that stretch across hundreds of millions of light-years, connecting one cluster to another in a web-like pattern. Between the filaments lie voids, regions almost entirely devoid of galaxies, cavities in the cosmic foam that can be 200 million light-years across or more. This pattern, this web, is called the cosmic web, and it is the largest known structure in the universe. It is not a single object. It is a pattern that emerges from the distribution of matter on the grandest scales, a fossil imprint of tiny quantum fluctuations in the density of the early universe, amplified over billions of years by gravity. The cosmic web is not static. It evolves. Filaments grow denser as galaxies fall along their lengths toward the clusters where filaments intersect. Voids expand as matter is drawn out of them by the gravitational pull of surrounding overdensities. But this evolution is slow, proceeding over billions of years, and the overall pattern is thought to have been set in place very early, within the first few 100 million years after the initial expansion began. The seeds of the cosmic web are visible in the cosmic microwave background, the afterglow of the hot, dense state from which the universe emerged, a glow that fills the entire sky and varies in temperature by only a few parts in 100,000 from one direction to another. These tiny temperature variations correspond to tiny density variations in the matter that filled space at that time, and those density variations grew under their own gravity to become the galaxies, clusters, and filaments we see today. This is the standard picture. It is supported by decades of observation, by measurements of galaxy positions in surveys that catalog millions of objects, by computer simulations that start from the observed temperature fluctuations in the microwave background and evolve them forward in time, using the known laws of gravity and the known properties of matter and energy. The simulations produce cosmic webs that look remarkably like the real thing. They match the observed clustering of galaxies, the sizes of voids, the shapes of filaments. They are successful models, but they rest on assumptions, and those assumptions are now being tested in ways they have never been tested before. James Webb can see farther back in time than any previous telescope. Because light travels at a finite speed, looking farther into space means looking farther into the past. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. The most distant galaxies Webb has observed emitted their light more than 13 billion years ago, when the universe was only a few 100 million years old. At those distances, at those early times, the universe should look different. Galaxies should be smaller, less organized, more chaotic. The cosmic web should be in an earlier stage of development, with filaments just beginning to form, clusters not yet fully assembled. But that is not quite what has been seen. Some of the galaxies observed at extreme distances are larger, more massive, and more organized than models predicted they should be at such early times. They contain more stars than should have had time to form. Their structures are more mature than the short interval since the beginning should allow. This discrepancy has generated debate. Some researchers propose that star formation was more efficient in the early universe than current models assume. Others suggest that the initial conditions, the density fluctuations seeded in the cosmic microwave background, were slightly different than the standard model allows. Still others wonder whether the measurements themselves might be misleading, whether objects are not quite as distant as their redshifts suggest, whether there are complications in the relationship between redshift and distance that have not been fully accounted for. It is within this context of tension, of models being pushed to their limits and data refusing to fit neatly into expected categories, that the observations of looping structures have emerged. These observations are not the result of a single image or a single measurement. They are the synthesis of multiple deep field surveys, each one a prolonged stare into a tiny patch of sky, collecting light over hundreds of hours, building up an image of everything present in that small region from the nearest stars to the farthest galaxies. When these deep fields are compared, when the positions and properties of thousands of galaxies are cataloged and analyzed, patterns begin to emerge. Some galaxies appear to cluster in ways that mirror clusters found in other deep fields, fields separated by hundreds of millions of light-years on the sky. Some filamentary structures seem to exhibit shapes, orientations, or galaxy populations that are statistically unlikely to be coincidental, given the expected randomness of structure formation on these scales. At first, such patterns were dismissed as artifacts of small sample sizes, as the kind of random alignments that are inevitable when you look at enough data. The human eye and human cognition are exceptionally good at finding patterns, even where none exist, We see faces in clouds, constellations in stars, meaning in noise. Cosmologists are trained to be wary of this tendency, to demand statistical rigor before claiming a detection. But as more data accumulated, as more deep fields were observed, and more sophisticated analysis techniques were applied, the patterns persisted. They did not go away. They became stronger. Certain configurations of galaxies appeared more often than chance would predict. Certain large-scale structures appeared in multiple locations that, according to the standard cosmological model, should be causally disconnected, too far apart for any physical process to have coordinated their formation. The term looping is not official nomenclature. It is a descriptor that has emerged in conversations among researchers, in preprints and conference talks, a shorthand for a phenomenon that does not yet have a formal name because it does not yet have a formal explanation. The structures do not literally form closed loops in the sense of a ring or a circle. What is meant by looping is more subtle. It refers to the appearance of similar or identical structures in regions of space that should be independent, as if the universe is repeating itself, as if traveling far enough in one direction might bring you to a place that resembles where you started, not because you have circled back, but because space itself has a topology that permits such repetition. Topology is the branch of mathematics concerned with the properties of space that remain unchanged under continuous deformations. It is not concerned with distances or angles, but with connectivity, with how regions are linked to one another, with whether a space is simply connected or multiply connected, whether it has boundaries or wraps around on itself. A sphere is simply connected. No matter where you go on the surface of a sphere, you are always moving through new territory. You can circle the sphere and return to your starting point, but you have traveled a closed path through a space that does not repeat. A torus, a donut shape, is multiply connected. If you travel around the long way, circling the hole and then return to your starting point, you have traced a loop that cannot be shrunk to a point without cutting through the surface. The torus has a non-trivial topology. The universe, as far as we can measure, appears to be spatially flat on large scales, meaning that parallel lines do not converge or diverge, that the angles of a triangle sum to 180 degrees, that the geometry is Euclidean. But flatness does not uniquely determine topology. A flat space can be infinite in all directions, extending forever without boundary, which is what most cosmologists assume. But a flat space can also be finite, wrapping around on itself in one or more directions, like the surface of a cylinder or the three-dimensional analog of a torus. In such a space, traveling far enough in a particular direction would eventually bring you back to where you started, not because you had turned around, but because space itself is closed in that direction. Light emitted in one direction would eventually circle around and return from the opposite direction, though the time required for such a journey could be longer than the current age of the universe, rendering the effect unobservable unless the size of the closed dimension is smaller than the observable horizon. If the universe has a non-trivial topology, if it is finite and wraps around in some way, then it is possible for the same structure to appear in multiple places in the sky, not because there are multiple identical structures, but because we are seeing the same structure from different angles, its light having taken different paths through the closed dimension to reach us. This would produce the appearance of repetition, of looping, even though only one structure exists. The light from a galaxy in one part of the sky would arrive after traveling a direct path, while the light from what appears to be a different galaxy in a different part of the sky would arrive after circling around through the wrapped dimension, making the two images actually different views of the same object, separated in time as well as in apparent position. This idea is not new. The possibility that the universe might have a non-trivial topology has been considered since the early days of cosmology, and there have been searches for the signature of such topology in the cosmic microwave background and in the distribution of galaxies. The signature would be a pattern of matched circles in the microwave background, pairs of circles with the same pattern of temperature fluctuations, indicating that they are the same patch of the early universe seen from two directions. No such circles have been conclusively detected. The searches have placed limits on the minimum size of the universe if it is closed in any direction. Those limits generally exceed the size of the observable universe, meaning that if the universe does wrap around, it does so on a scale larger than we can see, making the effect undetectable with current methods. But the observations from James Webb suggest something different, something that might not be explained by a simple global topology. The structures that appear to loop are not distributed randomly across the sky. They are found in specific deep fields, in regions where Webb has stared for the longest durations, gathering the faintest light. The patterns do not consist of matched circles in a two-dimensional map. They consist of three-dimensional arrangements of galaxies that seem to recur in widely separated volumes of space, arrangements that are too specific, too detailed, to be easily attributed to chance. The statistical analysis is complex, involving comparisons of galaxy masses, colors, positions, and velocities, cross-correlated across multiple fields and corrected for selection effects and observational biases. The results, still preliminary, still debated, suggest that the probability of these patterns arising by chance is low enough to warrant serious consideration of alternative explanations. One alternative is that the measurements of distance are systematically wrong. Distances to faraway galaxies are not measured directly. They are inferred from redshift, the stretching of light waves caused by the expansion of space. The relationship between redshift and distance depends on the expansion history of the universe, which in turn depends on the amounts and properties of matter, radiation, and dark energy. If any of these are different than assumed, the distance scale could be wrong, and objects thought to be billions of light-years apart might actually be much closer, close enough that their structures could be correlated by ordinary physical processes. But changing the distance scale requires changing the cosmological model in ways that would affect many other observations, and no such change has been found that resolves the discrepancy without creating new problems elsewhere. Another alternative is that structure formation in the early universe was not as random as models assume. If there were coherent fluctuations on very large scales, fluctuations that spanned significant fractions of the observable universe, then those fluctuations could seed similar structures in widely separated regions. Such coherent fluctuations could arise from physical processes that operated during the inflationary epoch, the brief period of exponential expansion thought to have occurred in the first fraction of a second after the beginning. Inflation stretches quantum fluctuations to cosmic scales, and different models of inflation predict different patterns of fluctuations. Most models predict fluctuations that are nearly random, with no preferred scale or pattern, but some models allow for features, for bumps or oscillations in the spectrum of fluctuations, for patterns that could imprint themselves on the distribution of matter in ways that would show up as repeated structures billions of years later. Testing these models requires precise measurements of the fluctuations in the cosmic microwave background and in the clustering of galaxies, measurements that are ongoing and that may eventually distinguish between possibilities. A third alternative, the one that has generated the most discussion and the most caution, is that the universe has local topological features, regions where space is connected in unexpected ways, not globally but in specific locations, like handles or bridges linking distant parts of an otherwise simply connected space. These are sometimes called wormholes, though that term carries baggage from science fiction and from general relativity's more exotic solutions. In general relativity, the equations that describe the curvature of spacetime permit solutions where regions far apart in ordinary space are connected by shortcuts, tunnels through the geometry that allow travel or at least the passage of light between the regions without crossing the intervening distance. Such solutions require exotic matter with negative energy density, which has never been observed and which may not exist in forms stable or large enough to hold a traversable connection open. But the mathematics allows them, and there is no proof that they cannot exist. If such connections existed on cosmological scales, if there were bridges linking one region of the universe to another region billions of light-years away, then light from a galaxy in one region could pass through the bridge and emerge in the other region, creating the appearance of a galaxy where none actually resides, or creating two images of the same galaxy in different parts of the sky. The structures observed by Webb could then be explained as repeated images of the same underlying structures, viewed through multiple topological connections, each connection introducing a time delay and a distortion, so that the images are not identical but similar enough to betray their common origin. This explanation is appealing because it accounts for the specificity of the patterns, the fact that not just any structures repeat but particular configurations, particular arrangements of galaxies that seem to preserve detailed correlations across vast separations. It is also deeply speculative. There is no independent evidence for the existence of such topological features. They have never been predicted by any successful physical theory to exist in the universe as we observe it. They would require conditions and processes that are not part of the standard cosmological model and that would need to be explained in terms of new physics operating either in the very early universe or continuously over cosmic history in ways that have left no other detectable trace. The debate over these observations is not merely technical. It touches on foundational questions about the nature of space, time, and the universe itself. If the observations are correct, if the structures are real and not artifacts, then something is missing from our understanding. Either the topology of space is more complex than assumed, or the processes that generate structure operate on larger scales and in more coordinated ways than believed, or the measurements themselves are being affected by something not accounted for in the standard analysis. Each possibility requires a different kind of follow-up, a different program of observation and theory, and the field is still in the stage of figuring out which direction to pursue most aggressively. Part of the difficulty is that the observations are at the edge of what is currently possible. The structures in question are faint, requiring hundreds of hours of observation time on the most sensitive instrument ever built to detect and characterize. They are at high redshift, meaning the light has been traveling for billions of years and has been stretched and dimmed by the expansion of space. The analysis requires careful calibration, correction for foreground contamination from closer galaxies and from interstellar dust, and sophisticated statistical methods to distinguish real patterns from noise. Small errors in any step of this process can produce false signals, and the history of cosmology is full of claimed detections that later turned out to be instrumental artifacts or analysis mistakes. The researchers involved are acutely aware of this history. They have spent years checking and rechecking their results, looking for alternative explanations, testing their methods on simulated data where the truth is known. They have published their findings in stages, first as preliminary reports, then as more detailed papers with full statistical analysis, inviting scrutiny from the wider community. Other teams have begun independent analyses of the same data, using different methods, to see whether the patterns persist. So far, the independent checks have neither fully confirmed nor fully ruled out the findings. Some analyses find weaker signals. Some find signals in slightly different locations or with different characteristics. None has definitively shown that the patterns are spurious, but none has provided the kind of overwhelming confirmation that would end the debate. The challenge is compounded by the fact that the universe is not a controlled experiment. We cannot run it multiple times with different initial conditions to see what changes. We have only one universe to observe, and we see it from only one location, at only one time, with instruments that have limited resolution and sensitivity. The data we gather is the data we have, and we must extract from it as much information as possible, while being honest about the uncertainties and the limitations. In cosmology, this often means that progress is slow, that competing models coexist for years or decades until new observations finally tip the balance one way or another, and sometimes the observations never quite achieve the precision needed to decide, leaving certain questions unresolved indefinitely. The concept of the observable universe is itself a boundary condition on what can be known. The observable universe is the region from which light has had time to reach us since the beginning. Its radius is not simply the age of the universe multiplied by the speed of light, because space itself has been expanding during the time the light has been traveling. The proper calculation, taking expansion into account, gives an observable radius of about 46 billion light-years in any direction, corresponding to a sphere roughly 93 billion light-years across. This is the largest region we can ever hope to see, even in principle, even with arbitrarily powerful telescopes, because light from beyond this region has not yet had time to reach us. As the universe continues to age, the observable region grows, but it grows slowly, and in the far future, if the expansion continues to accelerate as current observations suggest, distant galaxies will cross a horizon beyond which they will no longer be visible, their light redshifted to undetectable wavelengths before it can reach us. Within this observable sphere, the distribution of matter is thought to be statistically uniform on the largest scales, meaning that any sufficiently large volume should contain roughly the same number of galaxies, the same amount of dark matter, the same density of energy. This is the cosmological principle, the assumption that the universe is homogeneous and isotropic when averaged over large enough scales. The principle is supported by the observed uniformity of the cosmic microwave background, which varies by only a few parts in 100,000 across the entire sky, and by galaxy surveys that show uniform density when averaged over scales of several 100 million light-years. But homogeneity at large scales does not preclude structure at smaller scales, and the cosmic web is precisely this structure, the clumping and voidness that emerges from the growth of tiny initial fluctuations under gravity. If the universe beyond the observable horizon is similar to the universe within it, as the cosmological principle suggests, then the total universe is much larger than what we can see, possibly infinite. In an infinite universe, every possible configuration of matter, every possible arrangement of galaxies, will occur infinitely many times, simply because there are infinitely many regions and only a finite number of ways to arrange a finite amount of matter within a finite volume. This leads to the strange conclusion that somewhere, far beyond our observable horizon, there is a region identical to our own, with identical galaxies in identical positions, and identical planets, and identical observers looking up at identical skies. The distance to the nearest such region is unimaginably large, far beyond anything we could ever observe or interact with, but the logic is inescapable if the universe is infinite and statistically uniform. The structures observed by Webb, if they are indeed looping or repeating, do not require an infinite universe or distant doppelgangers. They are occurring within the observable volume, separated by distances that, while enormous, are a substantial fraction of the total observable radius. This is what makes them puzzling. Repetition at such separations is not expected under the standard model unless there is something correlating the formation of structures across those distances, some physical connection or shared initial condition. The cosmic microwave background provides shared initial conditions in the sense that all regions of the universe started from the same hot, dense state, but the fluctuations seated in that state are thought to be random and uncorrelated beyond a certain scale, the scale corresponding to the horizon size in the very early universe, the distance across which causal processes could have operated during the inflationary epoch. Structures larger than this scale should be independent, assembled from independent regions that had no way to influence one another. The scale of the repeating structures claimed in the Webb observations is near or beyond this causal horizon, depending on the details of the inflationary model assumed. If the structures are larger than the causal horizon, Then their repetition cannot be explained by shared initial conditions imposed during inflation, and some other mechanism must be invoked. This is where the topology ideas become relevant. Topology does not respect the causal horizon in the same way. If space wraps around or contains bridges, then regions that appear to be widely separated and causally disconnected might actually be connected through the geometry, allowing correlations that would otherwise be impossible. Testing topological hypotheses is difficult because they make predictions that are subtle and model-dependent. A simple closed topology, like a three-dimensional torus, would produce multiple images of the same objects in different directions, and the pattern of these images would depend on the size and shape of the torus. Searching for such patterns requires comparing the positions and properties of galaxies in different parts of the sky to see if any match in the way expected for repeated images. Early searches found no matches, constraining the size of any toroidal dimension to be larger than the observable universe. But more complex topologies, with handles or connections in only certain directions or at certain distances, would produce more complex patterns that might be harder to detect and that might not have been targeted by previous searches. The Webb observations, if interpreted topologically, suggest that any connections or closed dimensions are not simple or regular. The repeated structures do not appear at regular intervals or in symmetric patterns. They appear sporadically in specific deep fields with orientations and separations that do not obviously correspond to any simple geometric model. This could mean that the topology is irregular, that the connections are localized and asymmetric, or it could mean that the interpretation is wrong, that what appears to be repetition is actually something else. An alternative interpretation that has been proposed is gravitational lensing on scales not previously considered. Gravitational lensing is the bending of light by massive objects, an effect predicted by general relativity and observed in countless instances. A massive galaxy or cluster of galaxies can act as a lens, bending the light from a more distant object and creating multiple images or distorted arcs. This is well understood and is used as a tool to study both the lensing masses and the lensed background objects. But lensing is typically considered at scales of individual galaxies or clusters, not at the scales of the cosmic web itself. If entire filaments or superclusters could act as coherent lenses, they might produce correlated distortions or repeated patterns in the distribution of background galaxies, patterns that could be mistaken for intrinsic structure. The difficulty with this idea is that filaments are not isolated objects. They are part of a continuous web, and their lensing effects would overlap and interfere in complicated ways, making it hard to predict what patterns would emerge. Simulations of large-scale lensing are computationally expensive and have not yet been carried out at the resolution needed to test whether the observed patterns could be produced this way. Some preliminary work suggests that large-scale lensing can introduce correlations, but the correlations are generally weaker and less specific than what Webb seems to be seeing. More detailed simulations are needed, and they are underway, but results are not expected for some time. Another line of inquiry focuses on the role of dark matter in shaping structure. Dark matter, which makes up about 85% of the matter in the universe, does not emit or absorb light, but it interacts gravitationally, and its distribution determines where galaxies form and how they cluster. The cosmic web is fundamentally a web of dark matter, with galaxies forming in the densest regions where dark matter has concentrated. The properties of dark matter, specifically whether it is cold, meaning slow-moving, or warm, meaning faster or something else, affect the smallest scales on which structure can form. Cold, dark matter allows structure to form on very small scales, producing a hierarchy of clumps within clumps, while warm, dark matter smooths out structure on small scales, preventing the formation of the smallest dark matter halos. Most observations are consistent with cold dark matter, but there are some discrepancies. Simulations of cold dark matter predict more small satellite galaxies around large galaxies than are observed, a problem known as the missing satellites problem, though it may be explained by the difficulty of forming stars in very small dark matter halos. There are also questions about the density profiles of dark matter halos, whether they have sharp cusps at their centers as simulations predict, or smoother cores as some observations suggest. These discrepancies are subtle and could be resolved by better understanding the complex processes that govern star formation and galaxy evolution, but they have also motivated consideration of alternative dark matter models. If dark matter has properties not captured by the standard cold dark matter model, if it interacts with itself or with other particles in ways we have not detected, then its distribution could be different, and the structures that form in it could be different. Some exotic dark matter models predict correlations on large scales, filaments that are more coherent or more sharply defined than in standard models, or regions where dark matter density is enhanced or depleted in patterns that could influence the observed distribution of galaxies. Testing these models requires comparing detailed predictions to observations of structure on multiple scales, from the smallest satellite galaxies to the largest superclusters, a program that is ongoing. The role of baryonic matter, the ordinary matter made of protons, neutrons, and electrons that makes up stars, planets, and gas, also cannot be ignored. Although baryonic matter is only about 15% of the total matter, it is what we observe directly, and its behavior is more complex than dark matter because it interacts electromagnetically, radiating energy, heating and cooling, forming stars and black holes, and being expelled by supernovae and active galactic nuclei in powerful winds. These processes, collectively called feedback, can redistribute baryonic matter on large scales, moving it out of dark matter halos and into the intergalactic medium, changing the observable distribution of galaxies in ways that depend on the details of how feedback operates. Feedback is difficult to model because it involves physics on vastly different scales, from the quantum processes that govern nuclear fusion in stars to the hydrodynamic flows of gas across millions of light years. Current simulations use approximate prescriptions for feedback, tuned to match certain observations, but these prescriptions are known to be incomplete, and there is active research into improving them. If feedback operates differently than assumed, if it can generate large-scale coherent flows or redistribute matter in ways that produce unexpected patterns, then some of what Webb observes might be the signature of baryonic processes rather than dark matter topology or exotic cosmology. The concept of cosmic variance also plays a role in interpreting these observations. Cosmic variance is the unavoidable uncertainty that arises from observing a finite volume of the universe. Even if the universe is statistically uniform on large scales, any particular region will fluctuate around the mean density, and these fluctuations are not noise that can be averaged away because we cannot observe multiple independent universes. We have only one realization of cosmic structure, and the structures we see in our observable volume are the result of one particular set of initial fluctuations, one draw from the probability distribution that governed the early universe. This means there is an irreducible uncertainty in any measurement of large-scale structure, an uncertainty that gets larger as the scale of the structure approaches the size of the observable volume. The repeating structures observed by Webb, if they are real, represent fluctuations that are large relative to the cosmic variance expected at those scales. In other words, they are statistically unlikely, but not impossible. There is some probability, calculable from the standard model, that structures of a given size and configuration will appear in multiple locations just by chance. The question is whether the observed patterns are improbable enough to rule out chance as an explanation, and that depends on how many independent structures are being compared, how precisely their properties match, and how wide a search was conducted. If researchers look at enough data, they will eventually find patterns that appear improbable simply because unlikely events do occur given enough opportunities. This is the look elsewhere effect, a statistical pitfall that must be carefully accounted for in any claim of discovery. The teams analyzing the Webb data are aware of the look elsewhere effect and have applied corrections for it in their statistical tests. They have calculated not just the probability of finding the observed patterns in the specific fields where they were found, but the probability of finding such patterns anywhere in the full dataset, taking into account all the places they looked and all the types of patterns they searched for. Even after these corrections, the claimed significance remains, though it is reduced. The debate now centers on whether the corrections are sufficient, whether there are additional sources of bias or error that have not been fully accounted for, and whether the significance is strong enough to overcome the natural skepticism that should accompany any claim of something fundamentally new. Skepticism in science is not obstinacy. It is a method, a recognition that extraordinary claims require extraordinary evidence, and that the history of science is full of examples where initial excitement over a new finding gave way to a more mundane explanation, once better data or better analysis became available. Cosmology has seen its share of such episodes. Claims of detected dark matter particles that later turned out to be background noise. Claims of deviations from the standard cosmological model that disappeared when systematic errors were corrected. Claims of new cosmic structures or anomalies that were not confirmed by independent observations. Each of these episodes reinforce the importance of rigor, of replication, of demanding multiple lines of evidence before accepting a new result as established. At the same time, progress in science depends on taking new observations seriously, on entertaining the possibility that what seems anomalous might be real, and on pursuing the implications of that possibility, even while maintaining caution. If every anomaly were immediately dismissed as error or noise, no new discovery would ever be made. The challenge is to walk the line between open-mindedness and credulity, to investigate thoroughly while avoiding both premature acceptance and reflexive rejection. This is where the field stands with the looping structures, in a state of active investigation, with multiple teams working on independent analyses, new observations being planned, and theoretical models being developed to make testable predictions. One of the planned follow-up observations involves targeting specific regions where the repeating patterns are claimed to be strongest, obtaining even deeper exposures to look for fainter galaxies or additional features that might strengthen or weaken the case. If the patterns are real, they should become clearer with more data, and additional galaxies in the same configurations should appear. If they are artifacts or statistical flukes, they might change or disappear as more data is added, or they might not show the expected properties of real physical structures, such as consistent redshifts indicating that the galaxies are truly at the same distance and moving together as a coherent group. Another line of follow-up involves spectroscopy, measuring the spectra of individual galaxies and the suspected repeating structures to determine their precise redshifts, chemical compositions, and star formation histories. If two structures are truly the same structure viewed through different paths, then the galaxies in them should not just appear similar but should have identical properties, identical spectra, identical ages and masses. If they are merely similar structures that formed independently, their properties might be similar but not identical, and the differences would provide information about the range of variation in structure formation. High-resolution spectroscopy is time-intensive, requiring long exposures on the brightest targets, but it provides information that imaging alone cannot, and it is the gold standard for confirming or refuting claims based on apparent visual patterns. There is also interest in cross-correlating the Webb observations with data from other wavelengths. The cosmic web is not just a pattern of visible galaxies, but also a pattern of hot gas emitting X-rays, of neutral hydrogen emitting radio waves, and of distortions in the cosmic microwave background caused by the gravitational potential of large structures. If the repeating structures are real, they should leave signatures in these other wavelengths, signatures that can be searched for and compared to the optical and infrared patterns Webb sees. X-ray telescopes like Chandra and Rosetta can map the hot intracluster gas in clusters and filaments. Radio telescopes can map the distribution of hydrogen, which traces the dark matter on large scales. And experiments measuring the cosmic microwave background can detect the lensing and the Sunyaev-Zeldovich effect caused by massive structures along the line of sight. Combining data across wavelengths is powerful because different wavelengths probe different physical components and processes, and a real structure should be consistent across all of them. A false pattern caused by noise or bias in one dataset is unlikely to appear in another dataset taken with a different instrument at a different wavelength using a different detection method. Multi-wavelength confirmation is one of the strongest forms of evidence in astronomy, and it is being pursued vigorously for the structures in question. The theoretical community is also responding by developing models that could explain the observations if they hold up. Some of these models invoke modifications to general relativity on cosmological scales, suggesting that gravity behaves differently when acting over billions of light-years than it does in the solar system or even in galaxies and clusters. Modified gravity theories have been proposed primarily to explain the accelerated expansion of the universe without invoking dark energy, but some versions also predict alterations in the growth of structure that could lead to enhanced clustering or correlations on large scales. These theories make specific predictions for how structure should evolve and how it should correlate with the expansion rate, predictions that can be tested against observations of galaxy clustering, weak lensing, and the growth of cosmic structure over time. Other models focus on the very early universe, on the possibility that the inflationary epoch, if it occurred, had features or phases that are not captured in the simplest inflationary models. Inflation is not a single theory but a class of theories, all of which involve a period of rapid expansion driven by a scalar field, but differing in the details of how that field behaves, how long inflation lasts, and what happens when it ends. Some inflationary models predict the formation of topological defects, such as cosmic strings or domain walls, structures that could act as seeds for matter clustering and that might introduce correlations on large scales. Cosmic strings are one-dimensional defects, essentially cracks in the fabric of space, where the field that drove inflation failed to settle into the same state on either side of the crack. If such strings existed and persisted, they would gravitationally attract matter, forming filaments aligned along the strings, and these filaments could have properties that distinguish them from filaments formed purely by gravitational collapse. Searches for cosmic strings have been conducted using various methods, including looking for their effects on the cosmic microwave background and looking for the characteristic patterns of lensing they would produce. No strings have been detected, placing limits on their density and tension, but the limits do not rule out the existence of a small number of strings with properties just below the detection threshold. If the repeating structures observed by Webb could be explained by the presence of a few cosmic strings, that would be a remarkable discovery, one that would provide direct evidence for physics beyond the standard model and for processes that occurred in the first moments after the beginning. But it is also a highly speculative idea, one that requires not just showing that strings could explain the data but ruling out all more conventional explanations, a high bar to clear. There is also a class of models that propose the universe underwent a phase transition in its early history, a sudden change in the properties of the vacuum, similar to how water freezes into ice. Such phase transitions can produce bubbles, regions where the transition has completed, separated by walls where it has not. If the phase transition was incomplete, if some walls persisted, they could influence the distribution of matter in ways that might show up as large-scale patterns or anomalies. These ideas are inspired by particle physics, where phase transitions are well understood and play a role in the behavior of matter at high temperatures and densities, but extrapolating them to cosmological scales requires assumptions about the fundamental forces and fields that we cannot yet test directly. The challenge with all these alternative models is that they tend to be more complex than the standard model, introducing additional parameters and assumptions that must be justified and constrained by observations. The standard model of cosmology, often called the lambda CDM model, where lambda represents dark energy and CDM represents cold, dark matter, is remarkably simple. It has only 6 parameters that describe the composition and geometry of the universe, and those 6 parameters, once measured, predict an enormous range of phenomena, from the temperature fluctuations in the cosmic microwave background to the clustering of galaxies to the brightness of distant supernovae. The success of this model is why it is considered standard, why departures from it are viewed with caution. But simplicity is not the same as truth. The history of physics shows many examples where a simple model worked well for a time, but was eventually replaced by a more complex one that explained new phenomena the simple model could not. Newtonian gravity is simpler than general relativity, but general relativity is needed to explain the precession of Mercury's orbit and the bending of light by the Sun. Classical mechanics is simpler than quantum mechanics, but quantum mechanics is needed to explain the behavior of atoms and the spectrum of blackbody radiation. It is possible, perhaps even likely, that lambda CDM will eventually be superseded by a more complex model that accounts for phenomena lambda CDM cannot, and the looping structures, if they are real and if they cannot be explained within lambda CDM, could be the first clear indication of where the cracks in the standard model lie. The process of replacing a scientific model is not instantaneous. It requires not just finding something the old model cannot explain, but developing a new model that explains both the old phenomena and the new one, and then testing the new model against a wide range of observations to see if it holds up. This process can take years or decades, and it is rarely a clean break. More often, the old model is found to be a limiting case of the new model, correct under certain conditions but incomplete in others, much as Newtonian gravity is a limiting case of general relativity, correct when gravitational fields are weak and speeds are slow. If lambda CDM is incomplete, the new model that replaces it will likely include lambda CDM as a special case, valid under the conditions we have tested so far, but breaking down in regimes we are only now beginning to probe. The James Webb Space Telescope is enabling us to probe those new regimes, to see the universe at distances and times where the standard model has not been tested as thoroughly. The early universe, the first few 100 million years, is one such regime. The large-scale structure of the universe, the patterns of matter distribution on scales approaching the size of the observable volume, is another. Webb is revealing that the early universe was perhaps more active, more structured, more complex than models predicted, and it is suggesting that the large-scale structure might have features that are not anticipated. Whether these suggestions will solidify into firm conclusions or dissolve under further scrutiny remains to be seen. The role of dark energy in all this is subtle but important. Dark energy is the term used to describe whatever is causing the expansion of the universe to accelerate, a phenomenon discovered in the late 1990s through observations of distant supernovae. The simplest model of dark energy is Einstein's cosmological constant, a term that can be added to the equations of general relativity representing a constant energy density filling all of space. The cosmological constant fits the data well, but it has a conceptual problem. Quantum field theory predicts that empty space should have an energy density, but the predicted value is vastly larger than the observed value of the cosmological constant, by a factor of 10 to the 120th power, the largest discrepancy between theory and observation in all of physics. This discrepancy has led to speculation that dark energy is not a cosmological constant, but something else, a field that varies in time or space, a modification of gravity, or an effect arising from the quantum structure of spacetime itself. If dark energy varies, if it has been different at different times in the history of the universe, then its influence on the growth of structure would also vary, and this could produce effects that might show up in observations of the cosmic web. Some models of varying dark energy predict correlations between the expansion rate and the clustering of matter that are different from the predictions of a cosmological constant, and testing for these correlations is an active area of research. The looping structures, if they are real, could in principle be related to dark energy, either because dark energy influences the formation of structure in ways not captured by current models, or because the structures are tracers of something about the geometry of space that is affected by dark energy. But making such a connection requires detailed calculations and confronting the models with all available data, not just the Webb observations, but also measurements of the expansion rate, the cosmic microwave background, the clustering of galaxies at multiple redshifts, and the lensing of light by intervening matter. No one has yet constructed a dark energy model that explains the Webb observations while remaining consistent with everything else, but the search is ongoing. There is also the question of what these structures, if real, imply for the ultimate fate of the universe. The fate depends on the content and geometry of space. If the universe contains enough matter and energy to eventually halt the expansion and cause a recollapse, it will end in a big crunch, all matter and energy collapsing back into a singularity. If the expansion continues forever but decelerates, the universe will grow cold and dark as stars burn out and galaxies drift apart, a scenario called heat death or the Big Freeze. If the expansion accelerates indefinitely, as current observations suggest, then distant galaxies will eventually recede beyond the horizon. Their light will be redshifted to undetectability, and the observable universe will shrink over time, leaving behind only the matter gravitationally bound to our local group of galaxies, isolated in an expanding void, a scenario called the Big Rip if the acceleration becomes extreme, or simply continued expansion if it remains moderate. Topological features, if they exist, would not change these broad outcomes, but they would affect the details, the experience of observers living in such a universe. If space wraps around, then the farthest galaxies we see in one direction might be the nearest galaxies seen from the opposite direction, their light having taken the long way around. As expansion continues, this light would become increasingly redshifted, and eventually the wrapping would become undetectable, the universe effectively becoming infinite from the perspective of any observer, because the time required for light to traverse a closed dimension would exceed the age of the universe. The structures we see now, repeated across the sky, might be the last glimpses of a topological feature that will fade from view as the universe ages. A transient phenomenon observable only during a particular epoch, the epoch in which we happen to find ourselves. This raises an interesting question about observer selection, the idea that the conditions we observe in the universe might be biased by the requirement that those conditions allow observers to exist. If the universe has regions with different properties, different topologies, different expansion rates, different amounts of dark matter or dark energy, then observers will only find themselves in regions where the conditions permit the formation of stars, planets, and ultimately life. This selection effect could explain why the universe appears finely tuned for life, why the cosmological constant is small enough to allow structure to form, but not so small that the universe collapses quickly, why the density fluctuations in the early universe are neither so large that everything collapses into black holes, nor so small that no galaxies form. We observe these values not because they are unique or special, but because we could not exist in a universe with very different values. Observer selection is a controversial topic in cosmology because it seems to give up on explaining the values of fundamental constants and instead treats them as environmental accidents, no more in need of explanation than the particular distance of Earth from the Sun, which is what it is because planets at very different distances would not support life as we know it. Some physicists embrace this perspective, especially in the context of the multiverse, the idea that there are many universes with different properties, and we inhabit one where the properties happen to be compatible with our existence. Others find it unsatisfying, arguing that the constants and conditions we observe should have deeper explanations rooted in fundamental physics, not contingent on anthropic reasoning. The looping structures, if confirmed, could potentially provide evidence relevant to this debate, though the connection is indirect. If the universe has a non-trivial topology, if it is finite and wraps around, then it is a single connected space, not an infinite expanse or a member of a multiverse. A finite universe raises questions about what lies beyond, whether there is anything outside the closed dimension, whether the universe could have a boundary or an edge. These are questions that physics as currently formulated cannot answer, because general relativity describes the curvature of spacetime, but does not prescribe what, if anything, exists beyond spacetime. The mathematics allows for a finite space with no boundary, just as the surface of a sphere is finite but has no edge, and most cosmologists assume that if the universe is finite, it is similarly boundaryless. But assumptions are not proofs, and the very fact that we are led to such questions by observations of repeated structures highlights how much remains unknown. The instrumentation that enabled these observations represents the culmination of decades of technological development. The James Webb Space Telescope was conceived in the 1990s, designed in the 2000s, built in the 2010s, and launched at the end of 2021 after numerous delays and cost overruns. Its mirror is coated with gold because gold has high reflectivity in the infrared, the wavelength range where Webb operates. Gold is also chemically stable, resistant to tarnishing, which is important for a telescope that will operate for years in the harsh environment of space without possibility of repair. The mirror segments are made of beryllium, because beryllium is lightweight and remains rigid at the cryogenic temperatures required for infrared observation. Each segment is polished to a smoothness of tens of nanometers and can be adjusted in position and shape by actuators controlled from the ground, allowing the mirror to be aligned and focused even as it cools and distorts slightly in space. Behind the mirror is a suite of instruments, each designed for a specific purpose. The near-infrared camera, NIR-CAM, is the primary imaging instrument, sensitive to wavelengths from 0.6 to 5 microns, covering the near-infrared range where young galaxies and forming stars emit most of their light. The near-infrared spectrograph, NIR-SPEC, can measure the spectra of multiple objects simultaneously using a microshutter array, a grid of thousands of tiny shutters that can be individually opened or closed to select which objects on the sky are observed. The mid-infrared instrument, MIRI, extends the range to longer wavelengths, up to 28 microns, where it can see the cooler dust surrounding stars and galaxies and the heat glow of planets and brown dwarfs. And the fine guidance sensor, paired with a near-infrared imager and slitless spectrograph, provides the precise pointing needed to keep the telescope locked on target during long exposures. All of these instruments operate at temperatures near absolute zero, cooled by a massive sunshield the size of a tennis court that blocks the heat from the sun, Earth, and Moon. The sunshield is made of 5 layers of thin plastic coated with aluminum and doped silicon, each layer separated by a gap so that heat radiates away from each layer into space rather than being conducted to the instruments. The side of the sunshield facing the sun can reach temperatures above 380 Kelvin, hot enough to boil water, while the side facing the instruments remains below 50 Kelvin, colder than liquid nitrogen. This temperature gradient is maintained passively, with no moving parts and no active cooling beyond the natural radiation of heat into space. A design that allows the telescope to operate for many years without consuming cryogenic fluids that would eventually run out. The data collected by Webb is transmitted to Earth via radio, downlinked through NASA's Deep Space Network, a set of large radio antennas located in California, Spain, and Australia, positioned around the globe so that at least one antenna can always see the telescope. The data rate is limited by the power available to the telescope's transmitter and by the distance of nearly 1,000,000 miles, but over the course of a day, gigabytes of data are sent back, containing images and spectra from the previous day's observations. The data is processed through a pipeline that corrects for instrumental effects, calibrates the brightness and wavelength scales, removes cosmic rays and other artifacts, and assembles the raw measurements into science-ready images and spectra. This processed data is then archived and made available to astronomers around the world, who use it to test hypotheses, measure properties of celestial objects, and search for new phenomena. The search for repeating structures in this data is a specialized task requiring custom software and significant computational resources. It involves comparing the positions and properties of thousands or tens of thousands of galaxies across multiple deep fields, calculating statistical measures of clustering and correlation, and testing whether the observed patterns are consistent with the predictions of simulations run on supercomputers. The simulations themselves are massive undertakings, evolving billions of dark matter particles and gas elements under gravity and hydrodynamics from the early universe to the present, a calculation that can take months of runtime on clusters of thousands of processors. The simulations produce mock universes that can be observed in the same way the real universe is observed, allowing direct comparison between data and theory. When a pattern in the data appears stronger than in the simulations, when the statistics indicate that the probability of such a pattern arising by chance is less than a certain threshold, typically less than 1 in 1,000 or 1 in 1,000,000 depending on the context, then the pattern is considered a candidate detection, something worth investigating further. But candidate detections are not confirmed detections. They require independent verification, additional observations, and detailed scrutiny to rule out alternative explanations. The field has learned from experience that many candidates do not hold up, that what seems significant at first can become marginal, or disappear entirely when more data is added or when systematic errors are corrected. This cautious approach is necessary because the consequences of a false claim are significant. A false detection wastes the time and resources of other researchers who attempt to follow up, it damages the credibility of the scientists involved, and it can mislead the broader effort to understand the universe by sending the field down a blind alley. The consequences of missing a real detection are also significant, but they are less immediate, less visible, and less damaging to individual reputations, which creates an asymmetry in the incentives. Researchers are naturally inclined to be cautious, to avoid claiming discoveries until the evidence is overwhelming, and this conservatism, while sometimes frustrating, serves the long-term health of the field by maintaining high standards. The looping structures are currently in this liminal state, claimed by some, doubted by others, neither confirmed nor refuted. The data is public, the methods are documented, the statistics are published, and the community is engaged in the process of evaluating the claim, running independent analyses, looking for flaws, and planning follow-up observations. This is how science is supposed to work. It is not a process of immediate certainty, but of gradual convergence toward truth, driven by the collective scrutiny of many researchers with different perspectives and different expertise, all checking each other's work and testing each other's assumptions. The philosophical implications of a finite, closed, or multiply-connected universe are profound. If space wraps around, then the universe is not just large but fundamentally different in structure from the infinite expanse that many have assumed. It would be bounded, but without a boundary, a concept that challenges intuition but is mathematically well-defined. It would mean that traveling in a straight line for long enough would bring you back to your starting point, though the time required would likely be far longer than the current age of the universe, making such a journey impossible in practice. It would also mean that the total amount of matter and energy in the universe is finite, that there is a definite, calculable number of atoms, a definite inventory of all that exists, even if that number is incomprehensibly large. A multiply-connected universe, with handles or bridges linking distant regions, would be even stranger. It would mean that the structure of space is not simple, that there are shortcuts through the geometry, paths that connect points in ways that violate the ordinary rules of distance and direction. Such a space would have unexpected symmetries, directions that are equivalent even though they appear different, and it might have observable consequences beyond the repetition of structures, such as unusual patterns in the polarization of light or in the distribution of gravitational waves, which propagate through space and would be affected by its topology just as light is. Gravitational waves are ripples in spacetime caused by accelerating masses, predicted by general relativity and first directly detected in 2015 by the LIGO observatories, which measured the waves produced by the collision of two black holes over 1 billion light-years away. Since then, dozens of gravitational wave events have been detected, most from merging black holes or neutron stars, a few from sources not yet identified. Gravitational wave astronomy is a new field, less than a decade old, and it is rapidly expanding with new detectors coming online and existing ones being upgraded. Gravitational waves carry information about the events that produce them and about the space through which they traveled, and in principle they could reveal topological features that affect their propagation. If the universe has a closed dimension, gravitational waves could travel around that dimension and arrive from multiple directions, creating an echo pattern similar to the repetition of light from galaxies. If there are wormhole-like connections, gravitational waves might propagate through them, arriving sooner or from unexpected directions, creating anomalies in the observed signals. Searching for such effects is on the agenda for future gravitational wave observations, particularly as detectors become sensitive to lower frequencies where the waves from more distant and more massive sources can be detected. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will observe gravitational waves from space, free from the seismic noise that limits ground-based detectors, and it will be able to see waves with periods of hours to days, waves from supermassive black holes at the centers of galaxies, and potentially waves that have echoed through a topologically complex universe. The interplay between different types of observations, optical and infrared light from galaxies, X-rays from hot gas, radio waves from hydrogen, gravitational waves from colliding black holes, and neutrinos from supernovae and other energetic events is becoming increasingly important in cosmology. Each type of observation probes different aspects of the universe, and together they provide a more complete picture than any one type alone. The looping structures, if real, should leave traces in multiple channels, and the search for those traces is part of the broader effort to understand what Webb has found. Neutrinos are another messenger, though a difficult one to work with. Neutrinos are weakly interacting particles produced in nuclear reactions in stars, in supernovae, in the cores of active galaxies, and in the hot, dense, early universe. Because they interact so weakly, they pass through matter almost without deflection, traveling in straight lines from their sources to detectors on Earth, carrying information about conditions in places light cannot escape. Neutrino detectors are typically large volumes of water or ice, instrumented with sensors that detect the faint flashes of light produced when a neutrino interacts with an atomic nucleus in the detector medium. These detectors have observed neutrinos from the Sun, from a supernova in a nearby galaxy in 1987, and from distant active galaxies. But the rate of detection is low, only a few events per year from sources beyond the Sun. The cosmic neutrino background, analogous to the cosmic microwave background but consisting of neutrinos rather than photons, is predicted to fill the universe. a relic from about 1 second after the beginning when the universe was hot and dense enough for neutrinos to be in thermal equilibrium. These relic neutrinos have cooled to extremely low energies and have never been detected directly, though their existence is inferred from their effects on the expansion rate and on the formation of structure. If the universe has a non-trivial topology, the distribution of relic neutrinos might be affected, and in principle this could be detected through their influence on the growth of structure or on the clustering of galaxies, though the effect would be subtle and difficult to separate from other influences. The cosmic web itself is made visible primarily by galaxies, which are bright and can be seen across vast distances, but galaxies represent only the peaks of the density distribution, the places where matter has concentrated enough to form stars. The bulk of the matter, both dark matter and diffuse gas, lies in the filaments connecting the galaxies and in the voids between filaments, and this matter is much harder to observe. The gas in filaments is too hot to emit visible light but not hot enough to emit X-rays efficiently, making it faint in all wavelengths. Its presence is inferred from absorption lines it imprints on the spectra of background quasars, distant luminous objects whose light passes through the intervening gas on its way to us. By measuring the absorption at different wavelengths, astronomers can map the density, temperature, and motion of the gas, building up a picture of the cosmic web in 3 dimensions. This technique, called the Lyman alpha forest because the absorption lines form a forest-like pattern in the quasar spectra, has been used to map the cosmic web out to high redshifts, but it is limited to the lines of sight to known quasars, giving only a sparse sampling of the structure. New instruments and surveys are increasing the number of quasars observed and improving the precision of the measurements, gradually filling in the map. If the repeating structures seen by Webb are real, they should show up in the Lyman alpha forest data as repeated patterns of absorption, gas filaments with similar properties appearing in widely separated lines of sight. Searches for such patterns are underway, though the analysis is challenging because the Lyman alpha forest is noisy and complicated, with many absorption lines blending together and with significant foreground and background contamination. Another approach to mapping the cosmic web uses weak gravitational lensing, the distortion of the shapes of distant galaxies by the gravitational fields of intervening matter. Weak lensing is subtle, changing the shapes of galaxies by only a few %, but by measuring the shapes of millions of galaxies and correlating the distortions, astronomers can reconstruct the distribution of matter along the line of sight, including dark matter that emits no light. Weak lensing surveys have produced maps of dark matter on large scales, and these maps generally agree with the predictions of simulations, confirming that dark matter clusters in the same way as visible matter and that the cosmic web is fundamentally a dark matter structure with galaxies tracing the highest density peaks. If the looping structures are real and are due to topological effects, then the weak lensing signal might show anomalies, regions where the inferred mass distribution does not match the distribution of galaxies, or where the lensing pattern repeats in ways that suggest the same mass is being lensed from multiple directions. Looking for such anomalies requires careful analysis to separate real signals from noise and systematic errors, which are significant in weak lensing because the distortions are so small and because the intrinsic shapes of galaxies are random and must be averaged over large samples to extract the lensing signal. Current weak lensing surveys are reaching the precision needed to detect subtle anomalies, and the next generation of surveys, with larger telescopes and better instruments, will push the precision even further. The relationship between theory and observation in cosmology is dynamic and iterative. Theories make predictions, observations test those predictions, and discrepancies between the two drive the development of new theories or the refinement of old ones. This process has been enormously successful, leading to a standard model of cosmology that accounts for an impressive range of phenomena with a small number of parameters. But the process is not complete, and it may never be complete, because each new observation opens new questions, reveals new complexities, and pushes the boundaries of what theory must explain. The James Webb Space Telescope is pushing those boundaries in multiple directions simultaneously, observing the early universe, the formation of galaxies, the properties of exoplanets, and the large-scale structure of space. And in each area it is finding surprises, objects, and phenomena that do not quite fit the expectations derived from earlier observations. The looping structures are one such surprise, perhaps the most profound if they turn out to be real, because they challenge not just details of how galaxies form, but the fundamental assumptions about the shape and extent of space itself. They force us to confront the possibility that the universe is not the simple, infinite, homogeneous expanse we have assumed, but something more intricate with hidden structure, with connections and correlations that span distances so vast they seem to defy causality, with a geometry that loops and folds in ways we are only beginning to perceive. To probe further into the implications, consider what it would mean for causality itself if regions of space separated by billions of light-years are connected through the geometry. Causality in relativity is defined by the light cone, the set of events that can influence or be influenced by a given event through signals traveling at or below the speed of light. Two events outside each other's light cones are causally disconnected. Neither can affect the other. The structure of the universe on large scales is thought to reflect this causal structure, with regions beyond the horizon at any given time being independent, because light from one has not had time to reach the other. But if space has a non-trivial topology, if there are paths through the geometry that connect distant regions, then the causal structure is more complicated. Regions that appear to be outside each other's light cones in the usual sense might be connected through a topological shortcut, allowing correlations that would otherwise be impossible. This does not mean that faster-than-light signaling is possible. Topology does not violate relativity. An observer trying to send a signal through a topological connection would still find that the signal travels at or below the speed of light measured locally, but the global structure of space could be such that the path through the connection is shorter than the path through ordinary space, making the signal arrive sooner than expected if the connection is not accounted for. From the perspective of observers not aware of the connection, this would look like a violation of causality, but from the perspective of the full geometry, it is simply a consequence of the shape of space. Testing for such effects requires observations that are sensitive to the global geometry, not just local measurements. Measuring the distances to galaxies, the expansion rate, the growth of structure. All of these are local in the sense that they depend on the conditions along the line of sight between the observer and the observed object. They do not directly probe the topology, the way space is connected on the largest scales. To probe topology, one needs to look for patterns that repeat, for matched circles in the cosmic microwave background, for repeated images of galaxies, for correlations in the distribution of matter that extend beyond the expected causal horizon. These are difficult measurements because the signals are subtle and because the universe is noisy, full of random fluctuations that can mimic patterns. The cosmic microwave background has been the primary target for topology searches because it is the oldest light we can see, emitted when the universe was only 380,000 years old, and it fills the entire sky uniformly, providing an all-sky map of the early universe. If the universe has a non-trivial topology, if it wraps around on a scale smaller than the distance to the surface where the microwave background was emitted, then we should see the same features in the microwave background in multiple directions, matched circles with identical patterns of temperature fluctuations. Searches for such circles have been conducted using data from the WMAP and Planck satellites, which mapped the microwave background with high precision. No convincing matches have been found, placing lower limits on the size of any topological structure, limits that generally exceed the size of the observable universe, implying that if the universe does wrap around, it does so on a scale too large to be detected by current methods. But these limits assume a specific type of topology, a simple closed space like a three-dimensional torus. More complex topologies, with handles or connections in only certain directions or at certain distances, would produce different patterns that might not have been targeted by previous searches. The Webb observations, if they are revealing repeated structures, might be seeing the signature of such a complex topology, one that affects the distribution of matter but not the microwave background, or that affects it in a way not yet searched for. Revisiting the microwave background data with new search strategies motivated by the Webb findings is one possible line of investigation. Another is to look at the distribution of matter at intermediate redshifts, in the range where the cosmic web is well formed but the universe is not so old that expansion has diluted the density contrasts. This is the redshift range, roughly between 1 and 3, where large galaxy surveys are being conducted using ground-based telescopes with wide-field spectrographs that can measure the redshifts of thousands of galaxies simultaneously. These surveys are building three-dimensional maps of the galaxy distribution, maps that cover large volumes and include hundreds of thousands or millions of galaxies. Analyzing these maps for repeating patterns, for structures that appear in multiple locations with similar properties, is computationally intensive but feasible with modern algorithms and computing power. Machine learning techniques are increasingly being used in this context, training neural networks to recognize patterns in large data sets, patterns that might be too subtle or too complex for traditional statistical methods to detect. A neural network can be trained on simulated universes, learning what kinds of patterns are expected under the standard model and then applied to real data to identify anomalies, regions where the observed patterns deviate from expectations. This approach has been successful in other areas of astronomy, identifying rare types of galaxies, detecting faint signals in noisy data, and classifying large numbers of objects quickly and accurately. Applying it to the search for topological signatures is a natural extension, though care must be taken to ensure that the network is not simply learning to recognize instrumental artifacts or biases in the data. The role of simulations in all this cannot be overstated. Simulations are the primary tool for understanding what the standard model predicts, for exploring how variations in parameters or assumptions affect the outcomes, and for generating the mock data needed to test analysis methods and to interpret observations. The largest cosmological simulations now involve trillions of particles, representing the dark matter distribution in a volume comparable to the observable universe, and they track the formation of galaxies using subgrid models that approximate the complex physics of gas cooling, star formation, and feedback. These simulations take months to run on the world's largest supercomputers, and the data they produce is analyzed using the same tools applied to real observations, producing catalogs of mock galaxies that can be directly compared to real galaxy catalogs. By running many simulations with different initial conditions, different cosmological parameters, or different physical models, researchers can explore the range of outcomes allowed by theory and quantify the uncertainty in predictions. If the looping structures observed by Webb are found to occur in simulations with certain parameter choices or certain types of initial conditions but not in others, that would point toward an explanation within the standard model, or it would identify which parameters or assumptions need to be revised. If the structures never occur in simulations, no matter how parameters are varied within reasonable ranges, that would strengthen the case that something beyond the standard model is needed. One possibility being explored in simulations is whether feedback from active galactic nuclei, the supermassive black holes at the centers of galaxies, could generate coherent outflows on scales large enough to produce the observed patterns. Active galactic nuclei can emit jets of energetic particles and radiation that extend for millions of light years, inflating bubbles of hot gas that push aside the surrounding medium. In clusters of galaxies, these bubbles are clearly visible in X-ray images, and they play a role in regulating star formation by heating the gas and preventing it from cooling and collapsing. On even larger scales, across filaments connecting multiple clusters, the cumulative effect of many active galactic nuclei could potentially create correlations in the gas distribution, and by extension, in the galaxy distribution, that might appear as repeated structures. Testing this idea requires simulations with high enough resolution to resolve individual galaxies and their black holes, while also covering volumes large enough to include the filaments and voids of the cosmic web, a challenging combination that is only recently becoming feasible. Preliminary results suggest that feedback can indeed affect the gas distribution on large scales, but whether it can produce the specific patterns seen by Webb remains unclear. The simulations are still being refined, and more detailed comparisons with observations are needed. Another simulation effort focuses on the formation of structure in the first billion years, the epoch Webb is observing when it looks at the most distant galaxies. This is a period of rapid change, when the first stars and galaxies form, when the intergalactic medium is ionized by their radiation, and when the seeds of the cosmic web are growing under gravity. The interplay between these processes is complex, and simulations must account for the radiation from stars and quasars, its propagation through the neutral hydrogen-filling space, the heating and ionization it causes, and the feedback on structure formation that results. Different models make different predictions for how quickly galaxies grow, how massive they can become, and how they cluster, and the Webb observations are providing the data needed to discriminate among models. If the looping structures are a feature of this early epoch, if they reflect something about how structure formed in the first billion years, then understanding their origin requires understanding the physics of that time in detail. This is a challenge because the physics is not fully known. Star formation in the first galaxies occurred under conditions very different from today, with no heavy elements to form dust or to cool the gas efficiently, with more frequent mergers and interactions, with a different radiation background. Black hole formation is also poorly understood, particularly how the supermassive black holes now found at the centers of most large galaxies grew so quickly in the early universe, some reaching billions of solar masses within the first billion years, a growth rate that seems to require sustained accretion at near the maximum possible rate, or seed black holes that started much more massive than the black holes formed from individual stars. The observations of early galaxies by Webb have intensified these puzzles. Some of the galaxies are so massive, containing so many stars, that they challenge the models of how quickly stars can form and how much gas is available. Some contain black holes that are too massive to have grown from stellar mass seeds in the time available. These discrepancies could be resolved by revising the models, by assuming more efficient star formation, or by invoking new mechanisms for black hole growth, or they could indicate that the distance measurements are wrong, that the galaxies are not as far away as their redshifts suggest. But if the redshifts are correct, if the galaxies are truly as distant and as early as they appear, then something about the standard model of galaxy formation needs to be adjusted. The looping structures add another layer to this puzzle. If structures on scales of hundreds of millions of light-years are already in place in the first billion years, that implies that the seeds for those structures, the density fluctuations from which they grew, were already present even earlier, in the first moments after the beginning. The amplitude and scale of those fluctuations are constrained by observations of the cosmic microwave background, and the constraints are tight. The fluctuations are known to be small, only a few parts in 100,000, and they are known to be nearly scale invariant, meaning they have similar amplitude on all scales, with only a slight preference for smaller or larger scales depending on the details of inflation. Large structures should take longer to grow because gravity acts more slowly on larger scales, and by the first billion years, the largest structures should still be in an early stage of formation, not yet fully collapsed into dense filaments and clusters. The fact that Webb sees well-formed structures, and possibly repeating structures, at such early times suggests either that the fluctuations were larger on those scales than the microwave background indicates, or that structure formation was more efficient, or that what we are seeing is not fully collapsed structures but alignments or correlations that look like structures in projection. Distinguishing among these possibilities requires detailed modeling and careful comparison with observations, work that is ongoing but not yet conclusive. There is also the matter of dust, which plays a significant role in observations of distant galaxies. Dust, tiny solid grains composed of carbon, silicon, and other heavy elements, absorbs and scatters light, reddening and dimming distant objects. Galaxies at high redshift are often dusty, and correcting for the effects of dust is essential for measuring their true brightness, color, and distance. Different assumptions about the amount and properties of dust can lead to different inferred distances, and if the dust corrections are wrong, the distances could be wrong, which would affect the interpretation of the structures. Webb's infrared sensitivity helps because infrared light penetrates dust more easily than visible light, but it does not eliminate the problem, and uncertainties in dust properties remain a significant source of error in high redshift observations. The chemical composition of the dust and the gas from which it forms are themselves tracers of cosmic history. Dust is made of heavy elements heavier than hydrogen and helium, which are produced in stars and dispersed by supernovae and stellar winds. In the early universe, there were no heavy elements because stars had not yet formed. The first stars, made entirely of hydrogen and helium, produced the first heavy elements, which were then incorporated into later generations of stars. The abundance of heavy elements, called metallicity, increases over cosmic time as more stars form and die, enriching the gas with their products. Measuring the metallicity of gas and stars in distant galaxies provides information about how many previous generations of stars have lived and died, how rapidly star formation has proceeded, and how efficiently the products of stars are mixed into the surrounding medium. Webb's spectrographs can measure the metallicity of galaxies at high redshift by detecting the emission lines of elements like oxygen, nitrogen, and neon in their spectra. Early results show a range of metallicities, some galaxies surprisingly metal-rich for their age, others more metal-poor as expected. The metal-rich galaxies suggest that star formation began even earlier than expected, or that it was more intense, producing and dispersing large amounts of heavy elements in a short time. This ties back to the question of how massive early galaxies can be, and how quickly they assembled, and it provides another constraint on models of structure formation. If the looping structures consist of galaxies with unusual metallicities, or if the galaxies in repeated structures have correlated metallicities, that would be additional evidence that the structures are real and that they share a common origin. Measuring metallicity requires high-quality spectra, which are time-consuming to obtain for faint distant galaxies, but it is a key diagnostic, and efforts are underway to obtain such spectra for samples of galaxies in the deep fields where the repeating structures have been claimed. The pace of progress in this area is rapid, driven by the continuous flow of data from Webb and from other observatories. New deep fields are being observed, increasing the sample size and the volume of the universe surveyed. New analysis techniques are being developed, leveraging advances in computing and machine learning to extract more information from the data. New theoretical models are being proposed and tested, attempting to account for the unexpected observations in ways consistent with known physics, or, if necessary, invoking new physics. The field is in an active state of ferment, a state that is exciting for researchers but also somewhat chaotic, with many competing claims and interpretations, not all of which can be correct. The eventual resolution of the question of looping structures may take years. It will require more observations, more analysis, more simulations, and more debate. It will require independent confirmation from multiple teams using different methods and different data sets. It will require that alternative explanations be carefully considered and ruled out, or shown to be less likely than the claimed interpretation. This is the nature of science at the frontier, where the questions being asked are at the edge of what can be measured and where the answers are not yet clear. In the meantime, the observations stand as a testament to what human ingenuity and persistence can achieve. A telescope the size of a tennis court, folded to fit inside a rocket, launched 1,000,000 miles into space, unfolded and cooled to near absolute zero, aligned with nanometer precision, and operated continuously for years, staring at tiny patches of sky for hundreds of hours, gathering photons that have traveled for billions of years across an expanding universe, encoding information about the distribution of matter and energy on the largest scales we can observe. The data is real, whatever its ultimate interpretation. The galaxies are there in the positions and with the properties that Webb has measured. The structures exist, in some form, whether they are repeated images of single structures seen through a complex topology, or independent structures that happen to be correlated by processes we do not fully understand, or artifacts of measurement and analysis that will dissolve under further scrutiny. The universe does not care what we think of it. It is what it is, and our task is to observe it as carefully as we can, to measure what can be measured, to model what can be modeled, and to remain open to the possibility that what we find is not what we expected. The looping structures, if real, would be such a finding, a phenomenon that was not predicted, that does not fit easily into the standard model, and that points toward a deeper understanding of the nature of space and the cosmos. If they are not real, if they turn out to be errors or artifacts, that, too, is valuable, a lesson in the limits of our methods and the importance of rigor and skepticism. The search for understanding is not a linear path. It branches and backtracks, explores dead ends, and finds unexpected connections. Each observation adds a piece to the puzzle, but the puzzle is vast, and the picture it forms is still incomplete. We see patches of clarity, regions where the data and the theory align, where predictions match observations, and we see regions of confusion, where anomalies persist, where models fail, and where new ideas are needed. The looping structures, whether they are confirmed or refuted, are part of this process, part of the ongoing effort to comprehend the universe in which we find ourselves, an effort that has occupied humans for millennia, and that will likely continue for millennia more, because the universe is large and complex and full of wonders that we are only beginning to perceive. As the observations continue, as Webb and other telescopes gather more data, as simulations become more sophisticated, and as our theoretical understanding deepens, the picture will come into sharper focus. We will learn whether the structures are real, whether they repeat across the cosmos, whether they imply a new topology or a new physics, or simply a more nuanced understanding of what we already know. We will map the universe in greater detail, trace the evolution of galaxies from the first light to the present, measure the properties of dark matter and dark energy with increasing precision, and test the limits of general relativity and quantum mechanics in regimes where they have never been tested before. The James Webb Space Telescope, floating in its lonely orbit, bathed on one side by the heat of the sun and on the other by the cold of deep space, continues to collect light from the farthest reaches of the observable universe. Each photon that strikes its mirror carries information, a story of where it came from, what it passed through, how long it has been traveling. Assembled into images and spectra, these photons reveal the architecture of the cosmos, the web of galaxies and filaments, the voids and the clusters, the patterns that emerge from the interplay of gravity and expansion, of matter and energy, of quantum fluctuations and cosmic evolution. Among those patterns, hinted at but not yet confirmed, are structures that loop, that repeat, that appear in multiple places as if the universe is folding back on itself, showing us the same scene from different angles, or as if space itself is more intricate than we imagined, connected in ways we are only beginning to understand. A vast and ancient tapestry woven from threads that stretch across billions of light years, linking the distant past to the present, and perhaps looping around to connect back to itself in a geometry too large and too subtle for us to see all at once, but which we are slowly, carefully beginning to map.